Okay, whatever electrons in this valence band are bound electrons. Okay, here also electrons are there, but these are bound. Whatever electrons available in the conduction band, these are free. Okay, once these electrons leave the valence band, they leave the here. There is the empty space. Once this electron here going to a conduction band, so here there is no electron. That is leaving empty. That empty vacancy of electron we are calling a hole. What is the hole definition means? Vacancy of electron. If there is no electron, that we are calling a hole. Okay, only hole concept is we will discuss in semiconductors only. Okay, so if there is no electron, that means it is some hole is there. So these holes are free. Holes are free in valence band, and whatever electrons available in the conduction band, these are free. Okay, is it okay now? Okay, the gap between these two these two levels we are calling a band gap or energy gap. The band gap or okay, band gap, the gap between two bands, that is valence band and conduction band, that we are calling a band gap or energy gap. So depends on material, different material having different energy gap. Okay, is it clear now? For this is only just general semiconductor or intrinsic semiconductor. Okay, is it clear, everyone?
Yes, sir.
Yeah. Okay. Yes, sir. Okay. Now we'll go to the yesterday also we discussed this p-type n-type semiconductor, that is extrinsic semiconductor. Extrinsic means what? We are adding impurities. Suppose if you get some disturbance, please inform me. Here some net will be slow, so at home. So if any disturbance or any if my voice is not clear, just inform me. Okay, please let me know. Okay. So here in extrinsic semiconductor means we are adding some impurities to this semiconductor. Once why we are adding impurities to increase the conductivity. Whatever here intrinsic semiconductor, by increasing the temperature or by giving them thermal energy only, we are getting the conductivity, we are getting the current. Okay, so here but that is very less. So to increase the conductivity, to increase the current, we are adding some impurity atoms. Okay, if you add third group elements to fourth group elements, we'll get the p-type semiconductor. We'll get the p-type semiconductor. Okay, if you add fifth group elements to fourth group element, so we will get the n-type semiconductor. Okay, now we'll see how these are forming. Okay, just see 1 second. So here silicon, first we will see p-type, how the p-type is forming. Suppose silicon is a fourth group element, right? Silicon is fourth group element. Suppose in third group boron, aluminum, gallium, you can take any of them. Okay, here third group means 3 valency electrons are there. Fourth group means 4 valency electrons are there. Okay, right. So here silicon always makes a covalent bond with neighboring silicon atom by sharing. Covalent bond means each silicon share one electron, they make a bond. This is covalent bond. Okay, right. So like that, this silicon network is like this way. We can see. Okay, like this silicon. Many in a material there is a number of atoms. Okay, each atom is covalently bond with neighboring silicon atom. Okay, this is general silicon structure. Okay, here also the network is like this. It will extend up to okay many atoms. Okay, many atoms. Okay, now thing is here we are replacing this silicon with boron atom. We are adding boron atom here. Okay, so if you add boron atom, okay, boron is third group element, right? Third group element, that means it is only having 3 valency electron. 3 boron, it is having only 3 valency electron, right? But so these electrons share with neighboring silicon atom and makes a covalent bond. Covalent bond. This electron also shares with neighboring silicon and make a covalent bond. Okay. Here also one electron is there. This will also ready to make a covalent bond with neighboring silicon atom. Okay. 3 electrons of boron made a covalent bond with neighboring silicon atom. But here on silicon already there, but there is no electron here to make a bond with this silicon. So boron having 3 electrons, silicon having 4 electrons, each 3 sharing and making 3 covalent bond. But silicon having 4, but boron doesn't have one extra electron. So it is empty. So this empty we are calling a electron, sorry, hole. This empty we are calling a hole. Or so if you give some temperature or at moderate temperature, the covalent bond is breaking. Some covalent, these electrons are getting some energy and this bond will break. Okay, this electron fill this hole. Okay, fill this hole and they will make a covalent bond. Once this electron leaving this place means here hole will be formed. Like that, this hole will be filled by some other electron. Okay, like that, holes will be formed in this process. Holes will be generated in this process. These semiconductors we are calling p-type semiconductor. This type we are calling p-type semiconductor. And this silicon is the boron is ready to accept one electron, right? That's why we are calling acceptor. Okay, boron we are calling acceptor, right? So why we are calling acceptor? Boron is accepting one electron to make a covalent bond. That's why this is ready to this. That's why we are calling it acceptor. And in this process, in p-type semiconductor, majority carriers are holes. Majority carriers are holes, right? Did you understand this one? Hello.
Yes, sir.
You are silent. So got it right. So now we'll discuss next one, n-type semiconductor. We'll discuss n-type semiconductor. Okay. N-type semiconductor. So in this n-type semiconductor, please mute. Someone is unmuted. Okay. So in n-type semiconductor, how we are getting n-type semiconductor? Here we are adding fifth group element to fourth group atoms or elements, you can say. Here phosphorus, arsenic and bismuth, these are the example for fifth group element. Here silicon, germanium are the fourth group elements. Okay, here fifth group means 5 valency electrons are there. Here 4 valency electrons are there for near silicon atom. Okay, silicon element. Here also same thing. Here we are adding phosphorus. Here phosphorus having 5 valency electron. 5 valency electron, suppose like this. Okay, 5 valency electron, right? So this phosphorus also share one electron and makes a 4 covalent bond with neighboring silicon atom. Okay, neighboring silicon atom, it will make 4 covalent bond. Okay, like this. This is silicon. Okay, but this phosphorus having one extra electron ready to donate, but there is no silicon. Already 4 electrons of phosphorus made a covalent bond. 4 covalent bonds already formed. This extra electron is there for in phosphorus. So this is ready to donate. That's why this phosphorus we are calling donors. Phosphorus or fifth group elements we are calling donors. Okay, donors. So here, see here, this electron is ready to make another bond. So if you give some moderate temperature, the bond between the electron having also covalent, the electron also bind to this nucleus, right? This electron also, fifth electron also bind to nucleus. But if you give some moderate temperature, the moderate energy, electron, this breaks the bond with phosphorus. This breaks the bond and it will be free. This electron will be free. Okay, right? So if you give some temperature or moderate temperature, some of the covalent bonds break. This electron position and this will be free. Again, some will be like here electrons will be generated. Electrons will be generated without creating holes. Without creating holes, electron will be generated. Okay, right? So see, suppose here phosphorus having binding energy of 0.45 electron volts and silicon having binding energy of 0.05 electron volts. So this phosphorus, if you give some same energy, first electron will be break the bond in phosphorus, not in silicon, because the binding energy is higher in silicon. Okay, compared to phosphorus, here it is higher. So this electron, whatever fifth electron in phosphorus, first break the bond and it will become free. Okay, And after that, if you increasing the temperature, other covalent bonds also break and other electrons also free. Like that, we are creating free electrons in this process. This type of semiconductor we are calling N-type semiconductor. N-type semiconductor. Here, majority carriers are electrons. Majority carriers are electrons. Here we are not creating extra holes. We are not creating extra holes, only creating extra electrons. Similarly, in p-type also we are creating extra holes, not creating extra electrons. Okay. So only without creating other charge carriers, we are creating only one type of charge carriers in the process of doping. That is the advantage of doping. Only if you want a p-type, if you want electron, we add fifth group element. If you want a p-type, or if you want holes, you can add third group elements. Then you can create holes and electrons separately. Okay. Did you understand now?
Yes, sir.
Indu,
Yes,
did you
sir.
get? Indu, did you get it? Yesterday you are asking
Yes,
about. Is it clear today?
yes, sir.
Okay. So here depends on energy, the bonds are breaking and that will become a free. Okay, that is the thing. Okay, fifth group means 5 valence electron, that will 5 among 5 4 electrons will make covalent bond with silicon also 4 electrons are there, but phosphorus having one extra electron. At moderate temperature this electron will be free. That will free means that is breaking the bond and it become a free. That's why free electrons are available in this n-type semiconductor. Okay, now we will draw the energy level diagrams or energy, how the energy levels are there. Okay, now if you take intrinsic semiconductor. Okay, just I am writing shortcut semiconductor. Okay, these are the conduction band, this is the valence band. Okay, this we are calling a band, valence band. Okay, here valence band means you remember always, here many number of states are there, large number of states are there. By combining we are taking as a band. Here also in conduction band also many number of states are there. By all together we are calling a conduction band and all together we are calling a valence band. Okay, so here in intrinsic semiconductor only by temperature only we are creating free electrons. Okay, in the free holes in the valence band and free electrons in the conduction band, free electrons in the conduction band. That means, so here electron is breaking the bond in the valence band and jumping into the conduction band. So that means what? How many holes available in the valence band are equal to the how many electrons available in the conduction band. Electrons in conduction band equal to the holes in valence band, because once break the bond, electron is breaking bond and jumping into the conduction band by creating a hole in the valence band. So that is the equal number of holes in valence band and equal number of electrons in the conduction band are available. So that means Fermi level is middle of the band. Yeah, Fermi level is, this is Fermi level. What is that one? EF, Fermi level. What is the Fermi level? Anyone? What is mean by Fermi level? Anybody know definition? Fermi level? Fermi level. Anybody? Don't know? Hello?
At
Yes,
zero
sir.
temperature.
ఏది ఈరోజు మొత్తం సైలెంట్ అయిపోయారు మొత్తం? What happened? What is the definitions? You are saying something.
Energy
What is
at
the
zero temperature.
Fermi? Yeah, very good, very good. So maximum field energy level at 0 Kelvin. The Fermi level means the definition is maximum field energy level. Field energy level at 0 Kelvin. We have to mention Kelvin, 0 Kelvin. So at yesterday also we have discussed at 0 Kelvin all electrons will be will be available in the valence band. These these electrons are bound only, not free. At first definition is given at 0 Kelvin. 0 Kelvin. In that 0 Kelvin, all electron in the valence band only, right? But at room temperature only, some of the, see, if in case of intrinsic semiconductor, in the room temperature only, some of the electrons getting energy and jumping into the conduction band, right? That means, so half of the electrons available in the conduction band, half of the holes available in the valence band. That means it will, the Fermi level is middle of the band gap, middle of the band gap. Okay. But at 0 Kelvin, the Fermi level is here. At 0 Kelvin, Fermi level is here, right? But this is not, we are not staying at 0 Kelvin. We are staying at room temperature. That's why for intrinsic semiconductor, always we draw the Fermi level at the middle of the gap. Middle of the gap. That means what it indicates middle of the gap means number of electrons in the conduction band are equal to the number of holes in the valence band. That is the Fermi level in the middle means. Okay, right. Now we will draw
Sir,
the yes, Amma, please ask.
then Fermi level semiconductors acts as insulators, no sir?
Yes. Where it will act as insulator? 0 Kelvin. Suppose if you draw the, I am drawing here. So this is conduction band and this is valence band. If you want to draw the Fermi level at 0 Kelvin, the Fermi level is here only, right? This is Fermi level because all electrons will be available in the valence band only, right? There is no electrons here, no electrons available in the conduction band because all electrons bound to the nucleus in the conduction band only. This one at room temperature. Suppose room temperature we are drawing. That means about 27 degrees centigrade we are drawing. 27 means what? How much energy they will have? That K into T. Some K into T energy these electrons having. Once the electrons, the suppose silicon, if you take silicon if you take, how many valency electron? 14. Total configuration is 14, right? Electronic configuration, the atomic number. So here 3s n is equal to 3s or 3, if you take equal to this one, these whatever electrons in the available in the this shell are weakly bound compared to this one, right? That's why these electrons break the bond first and they will jump into the conduction band at room at when they get the some thermal energy. So that's why some of the electrons available in the conduction band, right? Now see here, at the definition is maximum field energy level at 0 Kelvin. 0 Kelvin we are defining the Fermi level, but our semiconductors, if you take any semiconductor, we are measuring the experiment, or we are measuring the conductivity, we are performing the device at room temperature mostly. That's why at room temperature some of the electrons also available. That means at 0 Kelvin Fermi level is at valence band, but if you increase the temperature, what happened? Some of the electrons jumping into the conduction band. That means Fermi level is also going up. Fermi level also going up. That is the region we are drawing at the middle of the band gap. Okay, is it clear, Indu?
Yes, sir.
At 0 Kelvin, it is available at here only, valence band only it is available, but we are not drawing most of the work or most of the measurement doing at room temperature. That's why we are drawing at middle of the band gap. Okay, Fermi level is going up. That means some of the electrons breaking the bonds and jumping into the conduction band. Okay, that's it. Now we will draw the same energy levels for P type and N type. Okay, P type and N type. Okay, we will see that one. Okay, just a second, please. So if you have doubts anywhere, you can please stop me and you can ask me. Okay, I am ready to explain. No need to worry. Okay, so now we are drawing p-type semiconductor. How it is looks like. Suppose here also this is conduction band and this is valence band. Okay, here also just you can draw. It's not a problem. Here this is a conduction band. Okay, this is conduction band. Here also large number of states are there. Here also states are there. So in conduction band, what are the majority carriers? What are the majority carriers in p-type semiconductor? What are the majority carriers in?
Holes.
Yes, holes means if you talk about p-type semiconductor, you have to talk with respect to holes. You have to discuss with respect to holes. So if you where you will get the holes, mostly holes where you will holes available in a p-type semiconductor in the valence band, right? In the valence band, holes are available. That's why you have to draw Fermi level close to the valence band, close to the valence band. Okay, please mute someone. Okay, so here also if you take n-type semiconductor here, if you take n-type semiconductor, this is the conduction band and this is the valence band. Okay, here also valence band holds there. In conduction band, free electrons are there, right? Free electrons in a different. So if you draw the Fermi level, you have to draw the, this is EC and this is EV. This is the Fermi level. Okay, this is conduction band. But lowest energy is, highest energy is EV. This is also some energy scale only, energy only. Like we have drawn one-dimensional potential box. If you draw, we have drawn, right. So if you draw the potential box, we have done E1, E2 till this one also. This is some energy, some zero energy. Let's take zero energy. This is one energy E1, and this is maximum energy is EV. Maximum energy in the valence band. In the valence band, is maximum energy is EV. In the conduction band, minimum energy is EC. EC is the minimum energy in the conduction band. Minimum energy EC. So this will extend up to infinity. Here also this extend up to infinity. These states are extend up to infinity. Here also these states are extend infinity in the negative scale, minus infinity, like that. So these also many states. Okay. So in p-type, the Fermi level is close to the valence band. In n-type, Fermi level is close to the conduction band. Okay, this is the difference. So if you take intrinsic semiconductor, Fermi level is middle of the band gap. If you take p-type semiconductor, Fermi level is close to the valence band, because in p-type, holes are the majority carriers. We have to draw the Fermi level correspond to holes only, with respect to holes only. So here in n-type semiconductor, Fermi level is close to the conduction band. That means it will, n-type means number of electrons. Number of electrons are higher in n-type. That's why we are drawing Fermi level close to the n-type semiconductor. Okay, is it clear now?
Yes, sir.
Here is it clear? So very simple. Just I will draw again once to get clear. So this is conduction band. As a drawing as a conduction band. Okay, this is the valence band. Okay. Valence band. This is EC. Maximum energy is EV and minimum energy is EC. And the band gap means this is the band gap between two energy bands. Gap between two energy levels. Lowest energy to highest energy. Okay. And
Voice clearly.
take the band, the middle of the band gap. Sorry. So if you take p-type semiconductor, Fermi level is close to the valence band. This is EF and this is EV and this is EC. Okay, EC. This is p-type semiconductor. Okay, here this is conduction band and this is valence band. Okay. If you take n-type semiconductor, same. The Fermi level is close to the conduction band. This is conduction band and this is valence band and this is the Fermi level. We are drawing close to the, this is EC, minimum energy in the conduction band. EV is the maximum energy in the valence band. This is the intrinsic, p-type, n-type. Okay, right? Now, see, thing is here also band gap means EC2, the difference between EG means what here? The energy difference between EC and EV. EC and EV. This is the band gap. Here also see the gap between two bands. Maximum of the valence band, minimum of the conduction band. This is the energy gap.